Hi, and welcome to our second set of notes on logarithms and derivatives. These notes, the sequel, part 2, is all about a topic that's called logarithmic differentiation. So you'll find these, I think, starting on page 8, maybe 8 or 9, at the bottom of page 8, from our notes from 4.3. Okay, so what is logarithmic differentiation? Let me just write my own sort of version of what this is. What happens with this technique, you start with a function, and I'm going to insert an adjective here. You don't just start with any function, you really start with usually a very weird function. And it's, I'll call it f of x. And what you want to find f prime of x. But because f is so weird, it's really hard to use our derivative rules. Now the weirdness here, the most common type of weirdness that we'll get, is this. F of x, what I mean by weird here, will be some function raised to the power of another function. So we'll see lots of examples of this in just a moment, right? But it's kind of weird to have like a function of x in the base and a different function of x all in the exponent. It's a weird combination. We don't really know how to differentiate this. And so what we do is we say, well, because this function is weird in this way, step 0, you don't ever have to take this step, but step 0 is to note that taking a logarithm, say a natural logarithm of f of x, makes an easier function. Right, so if we have, for example, what I have written up above in purple or pink or whatever, if f of x is like a function g of x to a p of x function, then I can use my power rule for logarithms. When I take the natural logarithm of this weird power, I can bring the power down out front. And now I can take a derivative of this new function, right? So this question says, here's a weird function f of x. Compute f prime of x. And the first step to take is actually to say, no, I'm not going to take a derivative of f of x. I'm going to first form the new function, the natural log of f of x, and then simplify this using log rules. And now differentiate this new function, the natural log of f of x. So, right, this is why it's called logarithmic differentiation. You're putting a log in front of your function, you're taking a log of your function, and then taking a derivative. And it turns out this isn't too hard to do, right? We already discussed this. The derivative of natural log is 1 over, and then we have to multiply by f prime of x. But I don't know what f prime of x is, because that's a weird derivative. However, this guy, right, would be our power times the natural log of g of x. So I'll be able to get a formula here. So this I'll be able to write out. And then my third step is get f prime of x all alone to get an answer to my original question. Okay, so these sort of red summary things, these steps, might make a little bit of sense, but I'm guessing they don't make too much sense. So let me do an example of this. It is the standard and coolest example to use. Let's start with the function f of x is x to the x. Now, if you hand this to somebody who's taking calculus and maybe forgotten it, or somebody who's just starting calculus, they might take a derivative of this by using the power rule. They might say something like f prime of x equals, you bring the power down, and then you do x to the x minus 1, something like that. But that's wrong, or at least we don't, if that's right, we don't know that we can use the power rule, right, for this function. The power rule works when we have the variable as a base and a constant as the power, as the exponent. Right, and so in this function you have a variable base and a variable exponent, so you can't use the power rule. Maybe you want to use the a to the x rule that we practice in the notes for 4.2. Some people might say, oh, I know what to do. This derivative should be, we should treat this as a to the x, and so that should be like the natural log of a, which is the natural log of x, times x to the x. Well, just like the power rule really didn't apply, this doesn't apply, right? So this was trying to think of this as a to the x, and that's not good. This was trying to think of this as x to a power, and that's not good. Right? So neither of those really apply, because it's not just a power, right? It's not x to a constant power, nor is it a constant to the power of x. It's both at the same time. And so one way to untangle this math is to say, well, geez, this is such a weird function. Rather than trying to figure out how to get f prime from this ugly function, let me form a new function. Maybe I'll even call it y. Y equals the natural log of f of x. And so that's the natural log of this weird combination. And I'll just bring that x down out front. And this doesn't look so bad. So it's these two, this expression and this last simplified one that I'm really going to work with, right? So my next step is now to say, okay, well, y prime is, well, the derivative of natural log of something is 1 over that something, and then I chain rule times the derivative. And now I go over to the second green underlined thing and I say, oh, but the derivative of x times natural log x, I know how to do that. That's just going to be a product rule. And so if you carry out the details here and simplify, you'll get 1 plus the natural log of x. So you've got to do the product rule there. This was actually an example we did last time. Okay, so we're almost done. Our goal, though, wasn't to find the derivative of what I called y. What we're asking for in this question is, what's the derivative of f prime? So I now want to solve this for f prime. And so really, all that requires me to do is multiply everything by the denominator, f of x. So I learned that f prime of x equals f of x times 1 plus x, oh sorry, 1 plus, I said that wrong, 1 plus the natural log of x. And we're pretty much done because the problem told us what f of x was. That's where we started. F of x is the function x to the x. So if you want, you can distribute this the derivative of x to the x is this function, x to the x plus x to the x times the natural log of x. Right, so this is the way logarithmic differentiation often works. You have a weird-looking function, and you sort of sneak up on its derivative by plugging your weird-looking function into a logarithm. I typically use the natural logarithm. You make your weirdness go away using logarithm properties. You differentiate, you rearrange, and suddenly you have the derivative of your weird function. So if I go back to my original guesses here, right, how somebody might think about trying to differentiate x to the x, well, you could imagine why somebody would say, I'm going to use the power rule, but that doesn't quite work. I'm going to use the a to the x, the exponential rule, that doesn't quite work, right? Neither one of these rules should apply because this function isn't 1. It's not a power function, it's not an exponential function, it's sort of a combination. But if you think hard about this, this formula we just got using logarithmic differentiation is actually these two things added together. Right? It's neither rule, but it's sort of both of them if you add both rules together. That's exactly what you'll get using logarithmic differentiation. Okay, that's just sort of a cool thing. I'm going to erase this little comment, though. You can think more about that if you like. I'm going to go back to saying, hey, that's wrong, that's wrong. Okay, so let's practice some logarithmic differentiation on a couple other examples. Okay, so this one has our steps written out for us, which is kind of nice. It says we're going to start with the function y equals x to the tangent of x. Whenever you see this again, whenever you see a function defined as another function raised to its second function power, that's a big sign you should use logarithms. So I'm going to take the natural log of both sides. It's going to be the natural log of y equals the natural log of x to the tangent x. And they have in step 2, hey, use your logarithm rules to simplify that stuff. So the logarithm rule I'm using is I can bring powers down out front. And now I can take a derivative of both sides. So the derivative of the left side, well, really, I should think about this, right, as the natural log of y of x. And so the derivative of that left side should be 1 over y of x times what I'm really after, y prime of x. And now I've got to differentiate tangent x times natural log of x. And so I'm going to have to do a product rule. That'll be the derivative of tangent times natural log plus tangent, times the derivative of natural log of x. And what do we have here? Well, the derivative of tangent, I'm sure everybody remembers, is secant squared. And for the second term, the derivative of natural log, I don't know why that happened with it too. The derivative of natural log is 1 over x. That's a weird looking expression, but okay. So now our last step, as I mentioned above, and as they're reminding us now, is to solve for what we're after, the derivative of the weird function. So I have that y prime is equal to y of x times this gigantic mess, secant squared of x times natural log of x plus the tangent of x all over x. And we just need to plug in what y of x was originally equal to. Y of x was equal to x to the tangent x. So here is an expression for the derivative of this weird function x to the tangent x. One thing that you'll notice probably, I mean your brain probably noticed it even if you didn't realize it was noticing it, is that when you start with these weird functions, their derivatives get worse. They get longer and involve the weird function again. Right? Said a little bit differently, when I ask for the derivative of x squared plus 1, I get a derivative that's really shorter, it's simpler, it's just 2x. But when I started with x to the tangent x and took a derivative, I got this giant mess, which is even longer and weirder. And that kind of makes sense. The thinking here is maybe if you start with a really weird function, its derivative could be even weirder. All right. So example 9 is really similar. So I hope it's okay if I go through this relatively quickly. So I'm going to say, okay, natural log y equals the natural log of x to the 2x plus 1. I can bring that power out front. And I have this. Nope, I guess that's step 2. Sorry, I did step 2 right there. And now I'm going to differentiate. The derivative of natural log y is going to be y prime over y. And the derivative of that stuff on the other side, I'm going to use the product rule. So the derivative of 2x plus 1 is 2. And the derivative of natural log of x is 1 over x. If you want, you can rewrite this. I don't know if this is especially better, but you can rewrite this as 2 plus 1 over x. I don't really know which way is especially better. Okay, but then we just have to solve for y prime. So y prime will equal y of x times this gigantic formula, which I'll write as 2 natural log x plus 2 plus 1 over x. And y of x, oh, I have to remember what that was. That was x to the 2x plus 1. Okay. So here are some more, here's another one. I don't know why they have this, it's sort of distracting me. So I'll let you guys look at your completed notes to try those. I don't really care about these. I want to look at this. Oh, I see. These are all, sorry, let me undo that. So these are examples for you guys to try. You can see how ugly they start to get. Maybe I'll work them out in a future video. But let's try this last one. We'll do this one together and then maybe we'll do a couple poppers. So this last one says find the slope of the tangent line to the curve y equals this really weird, terrible function of x at the point when x equals 2 pi. So the first thing to figure out is when x equals 2 pi, what is the y value? What point are we talking about? So y will equal 2 plus the cosine of 2 pi all to the 4 plus the sine of 2 pi. Okay, so we got to remember some trig. The cosine of 2 pi, that's the same thing as the cosine of 0, which is 1. So that's 2 plus 1 in parentheses. And that's all to the 4 plus 0. So that's 3 to the 4th, otherwise known as 81. So the point we're talking about is x is 2 pi and y is 81. Next we need the slope at this point. we want m, which is going to be y prime of 2 pi. So finally, the logarithmic differentiation part of this is going to enter when we want to figure out what y prime is. So I'm going to take a natural log of both sides. And what you'll see me doing is I'm going to go ahead and apply my log rule. I'm going to bring that power down, that's 4 plus sine of x, times the natural log of 2 plus cosine of x. Now when I differentiate both sides, I will get that y prime divided by y, and then I got to do a product rule here. The derivative of 4 plus sine of x is cosine of x, times the natural log of 2 plus cosine of x, plus 4 plus sine of x times, now I got to do the derivative of that natural log term. The derivative of natural log is 1 over the stuff inside the natural log, and then times the derivative of that inside function. So the derivative of 2 is 0, and the derivative of cosine is negative sine. Normally, this is where we would solve for y prime by multiplying through by y. In this question, though, because I'm going to plug in x equals 2 pi, I know that when x equals 2 pi, we already wrote down that y equals 81. So when I plug in x equals 2 pi, and I'll have to plug in y equals 81, I can get the slope at this point. So I will get that y prime over 81 is the cosine of 2 pi, which is 1, times the natural log of 2 plus the cosine of 2 pi, and cosine of 2 pi is 1, so that's 2 plus 1, that's 3. Then I get, over on this side, I'm just going to get plus 4 plus sine of 2 pi, so that's 4 plus 0, times the numerator is negative sine of 2 pi, which is just 0. And so that whole second term just becomes 0. So I get the natural log of 3. So y prime at 2 pi turns out to be 81 times the natural log of 3. And now maybe in purple I will end this. I'll say, okay, y minus y1 equals m times x minus x1. Y minus 81 equals, m is a weird number, 81 times the natural log of 3 times x minus 2 pi. This is a bizarre looking tangent line, but that's its equation. Alright, this is thankfully a shorter video. Let me throw in an extra page for a quick popper. Alright, so for our popper questions, so question 1 would be something like this. If f of x equals x to the 2x, then what is f prime of 1? I have to pause here to give ourselves some options for answers. So let's see. Sorry, I had to do some scratch work to give myself some good answers here. Let's see. Option A could be 0. Option B could be 1. Option C could be 2. Option D could be -1. And option E will be none of the above. Alright, so for a second question, let's actually make this a review about logarithms. Let's do it with natural logarithms. Oh, the natural log of x squared divided by 1 plus x squared has to equal a 2 natural log of x minus natural log of 1 plus x squared, b 2 natural log of x minus natural log of 1 minus natural log of x squared, c will equal natural log of 1 plus x squared minus 2 natural log of x, and d will just say is none of the above. Alright, let's try another popper question for this second part of notes. Alright. Let's do this. Which function, I'll call it g of x, has g prime of x equal to 1 over 2x. Give you guys some options here. So log base 2 of x. Oh, this one, maybe -1 over 2x squared. Maybe 1/2 natural log of x. And I guess I'll give you a couple more options just in case those aren't enough. Sure. Log of 1 over 2x. And then my last option will be none of the above. Okay, I know popper questions, especially at the very end, are kind of lame and boring. But okay, let's try this. Let's see. I am working hard to stay safe and calm during a very difficult time. And we'll just give you one answer choice for this. A, I hope so. Alright, and so the last one, let's just make the answer D. Alright guys, thanks for sticking with this video. I will have more uploaded soon. Stay safe and do the best you can do.